We will continue with our 11.2. Last time we already done with definition of infinite series, and we did one very big series that you encounter a lot in math called geometric series. And today I will continue with more topics, even though it seems to be 5 topics here, but the following actually are quite short. This guy here are quite short. What we have here, harmonic series, is just one special case that it is a special series that becomes a classical example for some case. But let's do telescoping sum first. What is telescoping sum? Telescoping sum is a technique to find the sum of a series where the middle terms cancel. Now, let's say, for example, I will use example from our book. This one is a well-known example, but we see a lot of such example there. Example 1 for telescoping sum. This is the example from the book. The sum of from 1 to infinity of the term 1 over 1 times n times n plus 1. Now, the thing is, if we rewrite this sum, this sequence, if we rewrite the sequence, we can use, if you remember partial fraction decomposition, right? Now, this is actually 1 over n minus 1 over n, actually n plus 1. You can try if you if you simplify these terms here. If you simplify these terms here, you combine them, have LCD. What you get here will be equals to this. Okay. Now then, for us to compute that, you will see that the first term in that parenthesis will be 1 over 1 minus 1 over 2 plus, this is when n equals to 1. This is when n equals to 1. When n equals to 2, that is 1 over 2 minus 1 over 3 all the way to, oh, you know what? Let me call that Sn first for now. The nth partial sum, which means I add only up to n. If I add only up to n, then the last term will be, I need to correct some of my notation here. Should be I there, so I equals to 1, I equals to 2, up to I equals to n.
Professor,
Uh-huh.
can you review for me really quick what the difference between I and n is in that?
Nothing. It's just notation. That's just indexing.
Okay.
It's just indexing. So I can change this. I can change this I to k here, and I'm still fine.
Okay.
Yeah, it's just notation. Yeah, okay.
But how does it, if I put n there, how would that differ?
Well, if you use n here,
If I put n as the n equals under the sum of the series symbol. Like,
the one here.
right.
Yeah, well, when you write n equals to 1, means your counter is n, right?
Okay.
But at the
Yeah.
same time, you need to count up to n. So you have two different definitions of n's in the same sentence. That's why it's not right. It's like this. It's like this. You may have seen this before, and I even penalize people for writing this. Like if you integrate from 1 to x of fx dx, this is not appropriate. Yeah, because x supposed to be the integral, the variable of integration, but at the same time, it is the limit of integration. You see this kind of notation when you apply fundamental theorem of algebra, fundamental theorem of calculus.
Okay.
Like, yeah, okay. Just to show you again. Let's say for example, let's say let fx equals to 3x plus 2. And then the question is, if fx equals to integral from 0 to x of fx dx. Now you see, then x here is a function for the integral supposed to be, so we cannot use x anymore here. So in calculus 1, your teacher is supposed to emphasize that it should have been written as ft dt, let's say.
Right.
Okay, yeah, so the variable of
Totally get it.
integration, yeah, variable of integration and limit of integration should not use the same variable. Now, the same idea here. It's just different definition.
Thank you.
Now, then what happened once we have this, series here, nth partial sum? Notice that this guy cancel this, right? And then this guy will cancel the term, the 1/3 after that. Okay, and keep on canceling, and you will see this get canceled too. So the sum, the nth partial sum is basically equals to 1 minus 1 over n plus 1. Okay, so so this sum from I equals to 1 to n of 1 over I times I plus 1 is equal to 1 minus 1 over n plus 1. So if I apply limit of n goes to infinity of this partial sum, nth partial sum, it will be limit n goes to infinity of 1 minus 1 over n plus 1. Okay, now the infinite sum, therefore, is equal to 1. Okay, now the technique is actually, you see that what I have in the first term, okay, being canceled, part of that being canceled by the second term, and the second part of the second term being canceled by the third term, so on and so forth. Okay, so this guy cancel, this get canceled, this get canceled, this get canceled. So in the end, I only have the first term and the last term. Oops. Like that. Okay, with unknown operation in between. But the middle terms actually cancel each other. That's why we call that telescoping. Okay, now for us to do telescoping, therefore, you need to know some partial fraction decomposition though. Okay, sometimes it's easier than that, but most problem actually requires you to know partial fraction decomposition. Let's say, for example, I pick question from the book, number 44. Number 44 on page 735. the sum of n equals to 1 to infinity of natural log of n over n plus 1. We want to find that the sum of this series. So we say let, maybe I use I this time as my sequence, as I be the ith partial sum up to I of natural log n over n plus 1. Okay. Our goal is later on this sum to infinity is equal to the limit I goes to infinity of Si. Is it right? Okay, that's what we want to do later on. But let's see what happened with the ith partial sum first. Now the ith partial sum will be, the first term will be ln 1 over 2 plus natural log of 2 over 3 plus natural log of 3 over 4 all the way to what? Natural log of
I
over I plus 1, right? I over I plus 1. Now the sum of log equals to log of sum. So this is, I'm sorry, log of product. So this is, if I put them together, there will be natural log of 1/2 times 2/3 times 3/4 all the way to I over I plus 1. Notice that this cancel, this cancel, this cancel, and you see that even the ith later on will cancel. So I get this is equal to natural log of 1 over I plus 1. Okay, so the sum of the series, the sum of the series from 1 to infinity of natural log of n over n plus 1, this is equals to the limit of I goes to infinity of the sum n equals to 1 to I of natural log of n over n plus 1. But that's the same to limit I goes to infinity of Si, right? Which is limit I goes to infinity of natural log of 1 over I plus 1. That is equals to the natural log of the limit, right? Which is equals to 0. Now, it is possible, however, the telescoping is not canceling with the next term directly. It is possible that the telescoping is actually happen in the next two terms. I think I happen to see that question here, number 48. Number 48. The summation of n equals to 2 up to infinity of 1 over n cubed minus n. So let's do partial fraction decomposition first. 1 over n cubed minus n equals to 1 over, I factor the n, I have n minus 1 and n plus 1. That's the factoring, right? Okay, so I get something over n minus 1 and n plus 1 with coefficients on the top. which if I multiply by the LCD, I get 1 equals to A times N plus 1. You can use X if you like, but of course you need to rewrite it first. This is N minus 1, N plus 1, N plus C times N minus 1. So when N equals to -1, there will be, this is 0, this is 0, that's 2C. So C equals to 1/2. When N equals to 0, 1 equals to -B. So B is -1. When N equals to 1, I get 2A. So A equals to 1/2. So now I can rewrite my 1 over N cubed minus N as 1/2 over N minus 1 plus, actually minus 1 over N plus 1/2 over N plus 1. Now that's what I will do here. This is the summation from 2 to infinity of 1/2 over N minus 1 minus 1 over N plus 1/2 over N plus 1. Am I doing okay so far?
Yeah.
Okay, now let's consider then the nth partial sum. Let as I, or you can use as K also. Let me use K this time. Is the kth partial sum, but the starting point, the starting n is actually not 1, but from 2. Okay, this is K here, not infinity. That's K there. Let me erase it first. That's a K here. And then 1/2 over N minus 1 times 1 over N plus 1/2 N plus 1. Which is equal to, if I kind of like write it out, then when N equals to 2, I get 1 over 2 over 1 minus 1 over 2 plus 1 over 2 over 3 plus, that's when N equals 2. When N equals 3, that will be 1/2 over 2 minus 1/3 plus 1/2 over 4. And so on and so forth. That's 1/2 over 3 minus 4 plus 1/2 over 5. All the way to the kth term. That's 1/2 over K minus 1 minus 1 over K plus 1/2 over K plus 1. Now let's see what cancels. Notice that this cancels here. These 3 terms cancel. Right? Okay. If I try to write more, let me write more here. Let me write more. This is 1/2 over 4 minus 1 over 5 plus 1/2 over 6. Notice that this guy with this guy with this guy cancels. You see that? Okay. Now all the way until I get 1/2 over n minus 1 minus 1 over n plus 1/2 over n plus 1. Okay, now as you expect, later on, this will cancel, right? And something cancel, blah, 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 all the way until this eventually will get canceled with something up there. Okay, something here.
So it has to be 3 terms, like the ones with 2's in the denominators don't cancel?
I will not say it that way. I actually see the pattern.
Okay.
Yeah, I actually see the pattern. So you see, this is half of 1/3. This guy here is half of 1/3.
Mm-hmm.
Okay, another half of 1/3 give you cancel this 1/3.
Ah.
Right? Do you see that?
Yeah, okay, I see what's happening there.
Okay. Now then, with quote-unquote telescoping, which is not perfect picture, perfectly the same to the way I explained telescoping here, but it's the same idea, right? It's like some terms in the middle cancel each other, right? Okay, so you see that the first 3 terms that was not canceled was these 3 here. Can use this color? No, I don't like this color. Go further down. Let me use this one. So the first couple terms that not cancel are these 3, right? Okay, and the last couple terms not cancelled are the one we have here. Okay, including 1 term up here. So if I rewrite it, then it will be the first uncancelled term is 1/2 over 1 minus 1/2 plus 1/2 over 2, and a plenty of things cancel in between, plus the last couple terms not being cancelled, which will be, what is the term that you see here? That will be 1/2 over n minus 1 plus 1. No, it's not supposed to be n, it's supposed to be k. Like that. It's supposed to be k. Because I use k up there. So this is k here. This is k. What happened with my pen today? So this is k minus 1 over k plus 1/2 over k plus 1. Okay, it turns out that the first 2 terms cancel. Okay, it just happened. Okay, it just happened. If it doesn't cancel, what do we do? Just compute it, right? So this is 0 plus 1/4, that's 1/4, plus 1 over 2k minus 1 over k plus 1 over 2 times k plus 1. Actually, I can simplify the middle 2 term a bit more. This is equal to 1/4 minus 1 over 2k plus 1 over 2k plus 2.
Wait, so how come, sorry, the one term at the very beginning, the 1/2 over k minus 1, how come it looks like it was being canceled out? Like by some previous term, it looked, was that
the
canceled?
one here?
Yeah.
Yeah. Okay, let's write down the previous term. The term right before the last term. The term right before the last term is 1/2 over k minus 1 minus 1. One half over k minus 1 minus 1 minus 1 over k minus 1 plus 1/2 over k minus 1 plus 1.
So
do you
then
see
how
that now?
come, yeah, but how come it was written at the bottom? How come it was included if it was canceled out? Like next to the 0 that you wrote?
Okay. No, that's not the one. That's not the one.
Oh,
Notice that the terms that get canceled here is this. This get
oh,
canceled. Like when I go this way, the middle
oh,
term right before that is this one,
mhm,
right? Now this guy here is canceled by the one before that.
mhm.
Okay, so the one I wrote down here is actually this guy. This guy. That's what I wrote there.
Oh, okay.
Okay. Now then, let me go on a bit further. So we have seen that the kth partial sum from 2 n equals to 2 to k of that expression 1 over n cubed minus n is equal to 1 over 4 minus 1 over 2k plus 1 over 2k plus 2. Now, I don't even want to simplify that, just leave it like that, because the next thing we will do is to take the limit, right? Limit k goes to infinity of sk will be limit k goes to infinity of this thing, which is equals to what? It's 1/4. Okay. Now to summarize then. So I really have problem with my pen today. The sum from n equals to 2 to infinity of that 1 over n cubed minus n is equals to 1/4. Okay, summarize your answer though. Okay, summarize your answer. Now that's for the telescoping part. That's for telescoping part. Now the following work is also considered as telescoping. The following method. The following. Oh, remember the proof that I gave you for the sum of geometric series? 1 plus x squared all the way to x to the n minus 1. If we call that the infinite sum of geometric series, then s times x is x plus x squared all the way to x to the n minus 1 plus x to the n. When I subtract this, notice that this guy cancel, this guy cancel, right? When I subtract, so I get s minus s times x equals to 1 minus x to the n. Now this method is already telescoping sum idea. Okay, so I multiply that s by some number such that the middle terms actually cancel. That's actually still telescoping. Okay, that's actually telescoping. But this is the first time I actually show you other way to look at the telescoping from the series point of view. Now, that brings us to the question that we already answered this question actually in algebra 2. The question of why is repeated decimal, a number with repeated decimal considered rational number.
Is it because it's a sum of rational?
Because it is a sum of, because we can rewrite it as fraction.
Right.
Because we can write it as a fraction. Suppose I pick question number 52. Number 52, write 0.46 bar as a fraction. Now notice that we cannot answer that question in any level before we learn geometric series. Okay, but once we learn geometric series, we can do this problem. We can show that this is actually a rational number. I can rewrite it as a fraction by doing it this way. Okay, suppose this is x. I show you the hard way first, okay, which is in line to what I teach you, what our lesson have here. Suppose this is x. This is 0.46464646 all the way. Now, somebody then say, oh, you know what, Thomas, this is 0.46 plus 0.46 times 0.01 plus 0.46 times 0.01 squared all the way. Now notice that we can rewrite this as the first term 0.46. The ratio is 0.01 to the k to the n minus 1 and from 1 to infinity. Do you notice that? So this is now equals to the first term 0.46 times 1 over 1 minus 0.01. Okay, the first term is 0.46. The ratio is 0.01. Okay, of course, we need to pay attention that it starts from 1 here, and this is n minus 1. Okay, but then when I compute this, this is 0.46 over 0.99, which is 46 over 99. That's the fraction. Okay, this is in line to the technique that we learned in this section from geometric series. Okay, but if you actually see even more, let me offer you another way to look at that problem. Is x equals to 0.464646 all the way. Now it repeats every two numbers. It repeats every two numbers. So let me multiply by 100 instead. If I multiply by 100, then the yellow 46 becomes 46 here. The blue 46 becomes here. The yellow 46 becomes here, and so on. Okay, so my yellow one becomes here. My blue one becomes, oops, my blue one becomes here. And my yellow one becomes here, so on and so forth, right? Now imagine if I subtract. When I subtract, I get 99x. I subtract backward, equals to 46. So x equals to 46 over 99.
Wow.
And it doesn't have to be this kind of number, though. This doesn't have to be this kind of number. It can be like the following. Let's say 2.3572 bar. What will this be in fraction? If I want to write this as a fraction, okay, call this x first. And let's make it repeating three numbers, 723, 723, 723. Okay, now because it repeats three numbers, I will multiply by 1000 such that the pattern 723 actually repeats. 23572. 23572. Now, if I multiply by 1000, then it will be 3273, like this, right? Then the digits will move 4 to the left. Is it 4? I think I'm missing something.
You'd have to.
I'm missing 5. I'm missing a 5. I'm missing a 5 here.
Right.
Yeah, 2, 3, 5. Okay. Actually, I moved three digits to the left. Okay. Now then,
Okay.
when
So
yes.
so when you multiply by 1,000, all you're doing is shifting all the digits over 1, 2, 3 over, and then that's no wait, that's 4 over.
Should be 3.
And then placing the decimal. Okay, I see what you're saying.
Yeah. Well, that's basically multiplying by 1000 case. If
Right.
you have 1, 2, 3.4, 5,
Yeah.
6, 7, 8,
You just
multiply
shift
by
the
1000, shift it 3 times, right? Okay, but now I write it in a way that the decimal point actually in line. Now then, when I subtract backward, I get 999 here, and the one here will be 2355. 4 point supposed to be 9 times 8, 8. So x is equal to 2354.88 over 999. Well, to make everybody happy, then I multiply the top and the bottom by 100. Now I have integer over integer, therefore this x is a fraction. I mean, is a rational number. Okay, of course you can simplify this though, but once I can write that as a integer over integer, I'm done with the question that it is a rational number. Okay, now I will go on to theoretical part. I'm done with the telescoping part, telescoping sum. Okay, now let's go to harmonic series. You need to memorize this series though. It's not hard to memorize. It's not hard to memorize. It's a very special series. That's a very special series that appear a lot as quote unquote counterexample. The sum of n equals to 1 to infinity of 1 over n. Okay, the claim is this is divergent. Is divergent. In fact, it's divergent to infinity. Okay, the proof you can read in the book. You can read the proof in the book, but the outline is basically like this. They say, or consider the partial sum. Maybe I don't want to fully follow that. Let me write it this way first. Consider partial sum as 1 equals to 1 over 1, as 2 equals to 1 over 1 plus 1 over 2, as 3 is 1 over 1 plus 1 over 2 plus 1 over 3, and so on and so forth. Now, notice that we all have the 1. Right? Now, the thing is, this part here, this part here, will be greater than 1, the blue part. How do you see that, Thomas? I see it this way. This is greater than the 1 from the yellow part. on the yellow part. Okay, and then for the blue part, it is actually greater than plus hmm, 1/4. This is 3/4. 1/4 plus 1/4 plus 1/4. Is it okay? I don't like that. Hold on. I really get annoyed with this. I make it like this. This is 1/2 plus 1/4 plus 1/4. That's from the yellow, from the blue part, and this is actually 1 plus. Let me make it as 2/2. Okay. Now the thing is, for S5 all the way to S8, it's 1/1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Now notice that this gives me 1. This gives me another more than 1. Maybe I use blue. This gives me more than 1. This is 1. This is more than 1. Okay. Now the thing is, this part here will be more than 1/2. That's more than 1/2. You can see this as the yellow part plus the blue part plus 1/8 plus 1/8 plus 1/8 plus 1/8. You see that greater than 1/2?
Partner, can I ask a quick, can I ask a quick question?
Okay.
Okay, so the S4 line, I don't get what happened after the greater than sign.
I changed the 1/3 and 1/4. I changed that 1/4, 1/3. I changed this guy here. 1/3 is greater than 1/4.
Right.
Right?
So in order to make that correct, you had to change one so that it would go down.
I just tried to show you that S4 is greater than certain number. S4 here, the sum of the first 4 partial term is greater than 2. And S8 later on will be greater than, S8 later on will be greater than 1 plus 3/2. And if I continue the procedure even further, you will see S16 is greater than 1 plus 4/2. In general, you will see, I really get annoyed with the, I'm sorry. I really get annoyed with my pen. Basically, S to the 2k, S of 2 to the k is greater than 1 plus k/2. Basically, eventually, as long as you pick enough number of terms, okay, as long as you pick enough number of terms, you will get a sum which is greater than whatever number you chose earlier. Now the thing is this 2 to the kth partial sum is greater than 1 plus k over 2, such that when you apply the limit k goes to infinity, limit k goes to infinity, and Sn will go to infinity because it's bounded below by infinity. Now that's the idea of the proof there in our book. That's the idea of the proof. Is if you add enough number of terms, then there must be some whatever number you choose. Let's say you choose 5. Okay, you want to choose 5. You say, oh, you know what? How many terms do I need to add to get more than 5? Then yeah, you will add 1 over 1, 1 over 2, all the way to, let's say 5. Then it will be 5. So you need to add up to 1 over 2 to the 9th terms. Then this sum here will be greater than 5. What happened with my... If you choose 15, then I can find some number furthermore I can add to that the sum is more than 15. So whatever number m you choose, for every n you choose, there is a k such that the kth partial sum is greater than that n. But see what happened? I just moved my pen and that's what happened right away. You know what? Let's see. See? Anyway, but this is the definition of divergent to infinity though. This is the definition of divergent to infinity. Whatever, I don't do anything. I got frustrated. Well, anyway, so if you want to see more details on the explanation, you can see your book. It is on page 732. That's the proof is on page 432 that this series is divergent. Now the thing is, this series has a special name called harmonic series. It refers to the sum of 1 over n from 1 to infinity. I really get out of patience with my pen. I think I know. Anyway, now why I need to mention this harmonic series? Because of the following. Note that in harmonic series, is divergent even when 1/n converges to 0. Even if this sequence here, convergent to 0. Okay? Yeah, even when that convergent to 0. Now, what I'm trying to say is this. What I'm trying to say is, if, you know what, let me give myself a break. We come back at 5, right now it's 22, give me 10 minutes approximately, 35. We come back at 5:35. Okay, let me continue. See, I get so distracted. Now we see one thing that first, suppose we have a series that is convergent. If a series is convergent, then we know that the last term, limit n goes to infinity of the a sub n, the last term should be 0. The limit of the last term should be 0. Okay, because otherwise, suppose limit n goes to infinity of n is not equals to 0, then when you go to infinity here, you keep on adding something non-zero, right? You keep on adding something non-zero. So basically, limit of n goes to infinity of s sub n minus 1 plus limit n goes to infinity of a sub n. It's supposed to be limit n goes to infinity of s sub n. Because the nth term is equals to the previous term plus the last term, the nth term. Okay, so that's what happened. Now the thing is, when it is convergent, then this sum here should be the same to that sum. Ah, man, I get so pissed off right now. I'm sorry. Okay, now suppose they are the same limit, L and L here, then the limit here has to be 0. Okay, let me try to write the proof in a more organized way. I'm super distracted with my pen. Suppose we know that proof it is known that the sum of the nth partial sum is the n minus first partial sum plus the nth term. We also know that then when I apply the limit, n goes to infinity of s sub n, the n partial sum will be limit n goes to infinity of s n minus 1 plus limit n goes to infinity of a sub n. Now, since the infinite sum, the infinite series is convergent, and we say it is convergent to, let's say L go to L, then we will get infinite series. This guy here will be equals to L equals to limit n goes to infinity of, oh, actually this one also goes to L, this also go to L, plus limit n goes to infinity of the end, the last term basically. Now from here then we see that it implies limit n goes to infinity of a sub n, the nth term, when n goes to infinity it should be 0. Okay, now, but simply because the last term, the sequence goes to 0, it does not imply the series will be convergent. It's necessary but not sufficient. The limit of the sequence goes to 0 is necessary for the series to be convergent, but not sufficient, not enough. Why? We have seen through a note that the harmonic series is divergent even when 1/n, the sequence actually convergent to 0. So differentiate the sequence and the series. The sequence may be convergent to 0, yet the series not convergent to any number. Okay, it goes to infinity instead. Okay, now because harmonic series is divergent, then any multiple of harmonic series will also be divergent. Please take a look on the theorems on page 733. There's a box there. Some theorems to see that if series for A and series for B are convergent, then first the sum of constant multiple of the sequence is equal to constant multiple of the series. Now, mimic this with integral of CFX dx is equals to C times integral fx dx. You can mimic that because integral is basically summation also. Okay. Now, second, the summation of sum of two sequence, or even the difference of two sequence, is equals to the sum of the series. Okay, but keep in mind, it is only true if those two series are both convergent. If they are not convergent, we cannot split them. Okay, if they are not convergent, we cannot split them. Okay, if they are not convergent, we cannot split them. Now, last part is interval of convergence. Interval for convergence. Now we will learn about interval of convergence a lot more later in later sections, but right now we can already start working on that. For example, the following question: find the values of x. Find the values of x for the series to be convergent. Let's say I do number 58. Let's say I do number 58. The series from 1 to infinity of x plus 2 to the n. Now this has the pattern of a geometric series. Okay, let me rewrite it into geometric series. This is the sum from 1 to infinity of x plus 2 times x plus 2 to the power of n minus 1. Right? In which from here we see, you don't need to show the work this way though, but I try to show you the idea behind this. The first term will be x plus 2, and the ratio is also x plus 2, right? Okay, now we know that a geometric series is convergent when the ratio, the absolute of the ratio is between, less than 1. The absolute of the ratio is less than 1. Basically, this r here has to be between -1 and 1. You see? And that's what I do. So to find the x such that this geometric series is convergent, what my x can be, then x plus 2 has to be between -1 to 1, subtract by 2, so x has to be between -3 to -1. Okay, so the solution will be x has to be in that interval. That's for number 58. Now, how about, for example, number 40? I'm sorry, number 60. The series from 0 to infinity, you will see the 0 doesn't matter, of -4, what did I do? -4 to the n times x minus 5 to the n. Notice that I can rewrite this as n equals 0 to infinity of -4x plus 5 to the n. No, not plus 5, plus 20. Now notice that from here we see that the r is -4x plus 20, right? And that guy has to be between -4x plus 20, has to be between -1 and 1. Subtract by 20. divided by -4. So 21/4 should be greater than x, should be greater than 19/4. So the series n equals to 0 to infinity of -4 to the n x minus 5 to the n is convergent when x is between 19/4 to 21/4. Okay. Your suggested homework from here will be this is 11.2. I asked you to do some already, but I would like you to do more. Number 33. Up to number 63. Okay, that's for your 11.2. .3. 11.3 on the integral test and the estimate of sum. Now, I think I need to write this as a note first. Note that we have learned one geometric series is convergent when the ratio, the magnitude of ratio is less than 1. Okay. Second, we have also learned something called harmonic series. Harmonic series is divergent. Okay, now the thing is, the series that we will be dealing with, not only geometric type, not only harmonic type, but other type. Now in this section 11.3, we will see other method to show if a series is convergent or divergent. And that method is called integral test. Now, the idea for integral test is as the following. We will, when we get the sum, let's say consider, let the sum of n equals to 1 to infinity of a sub n, if we rewrite it as a sub 1, a sub 2, a sub 3, all to infinity, and we see this, we define this to be f1, f2, f3, all the way, then we can see that as the following. Suppose a1 is here, and n equals to 1 is here, when n equals to 2 is here, when n equals to 3 is here, n equals to 4 it's here, so on and so forth. Now, how do we add this? How do we add these dots here and find the sum? Now, one way is to imagine the following. One way to imagine that what we need to add is actually the area of this thing. You know, go back. I want to use this. I want to add this plus I want to add this plus I want to add this all the way. Okay, now I want to find the total area of those highlighted boxes. But the total area of those highlighted boxes apparently is more than the area under the curve here. If I connect these dots, notice that the sum of those boxes, is greater than the integral under the curve greater or equals to the integral under the curve of fx, if I call that fx, from 1 to infinity of fx dx. Now, please think about that first, at least from the picture. You see from the picture that the sum of all these boxes here, the sum of this box, the area of this box plus the area of this box plus the area of this box plus the area of this box and so on and so forth will be greater than the integral, because the area under the curve will refer to only this section here, right? You see what I mean? So the sum of those boxes have extra here, 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 and on. You see what I mean? Now, on the other hand, I would like to copy this graph. I want to copy this graph here. I want to copy that graph there and see another point of view. I want to do the following. I will erase this guy. Okay. And then I will move this guy here, the blue one here, to the left. I'll move the blue one. I wonder if it is doable. Yeah, seems like it's doable. To the left. Oops, something got cut. No, that's not what I meant. Let's do it this way then. Now you see that the integral from 1 to infinity of fx dx is greater than the summation of the terms from the second term, because the height here is the same with the second term. This is A2. This is A3. Why? This is A3. Okay, so from the picture we have above, this guy here, and the picture we have below here, we see the following situation, that the series of A sub n will be divergent, if integral from 1 to infinity is divergent. If this is divergent, then this guy will be divergent. Because the series is bounded below by something infinity. Maybe I write that here. Since what did I do? Since integral of 1 to infinity of fx dx is less than equals to the series, again, from 1 to infinity, then, yeah, because it's bounded below by the integral, right, from 1 to infinity, because it's bounded below by the integral from 1 to infinity, then if the integral is divergent to infinity, then the series must be divergent. Now, on the other hand, since the summation from 2 to infinity of A sub n is less than equals to integral from 1 to infinity of fx dx, and adding the first term will make it the full series. Then we see the sequence, I mean the series will be convergent, is convergent if the integral is convergent. Okay. Now, with that said, then we come up with integral test. Integral test. Now, the integral test says the following. Let the series a sub n from n equals to 1 no. Let a sub n be a sequence and fx be the continuous superposition function and that fx is positive. Fx is positive. We want that to be continuous and decreasing. Okay, when I say continuous superposition function, it implies that Fn equals to the n term. Okay, now then, the series and the integral are both convergent or both divergent. Okay, now I want to add one emphasis that actually they don't need to be strictly positive and strictly decreasing. We just need eventually. Okay, we just need eventually. If the continuous superposition function is eventually positive and eventually decreasing, then the integral and the series must be both convergent or both divergent. Now, let's say, for example, the first example for this section. This one is the series of what is good? 1 over n squared plus 1 convergent. Now then, what I will need to do is let fx equals to the continuous superposition function of the sequence. Okay, I need to show that, let me claim, I need to show that first, the fx is decreasing, and second, the fx is positive. I think the second one is easy to do. So I will claim first, fx is decreasing. This is kind of like our cheat sheet here, what I need to show. Okay, now claim that fx is decreasing. How do you show that a function is decreasing? What I think I will do is I will do the derivative. The derivative of fx equals to and that will be negative 2x. Now notice that this is negative for x greater equals to 1. Right? Well, because the denominator will always be positive. Right? I missed a square. The denominator is always positive. Okay? Now, so because the denominator is always positive, then it will be the first derivative will be negative for as long as negative 2x, the numerator is less than 0. So x is greater than 0, right? Okay. Now, of course, when it is 1, then it is okay, right? Now, second, I need to show that it is positive, but I think that one is actually clear. That fx is positive. That one is clear. 1 over x squared plus 1 is always positive because x squared plus 1 is always greater or equals to 0. Actually, just strictly greater than 0. Now, once you can show that this continuous superposition function is decreasing and positive, then what I will do is I will show the integral. Now, integral from 1 to infinity of 1 over x squared plus 1 dx is equals to limit t goes to infinity from 1 to t 1 over x squared plus 1 dx. This is limit t goes to infinity of tangent inverse x from 1 to t, right? So this is limit t goes to infinity of tangent inverse t minus tangent inverse 1. What is tangent inverse 1?
Pi over 4.
It's pi over 4. And how about tangent inverse infinity?
Pi over 2.
That's pi over 2. So because the integral is finite, okay, convergent, then you need to say which test you use by integral test. And you need to explicitly say which series you are talking about. This series is convergent. Okay, now one big thing though, one big thing. I myself have this misunderstanding before. Notice that this integral test says that they are both convergent or they are both divergent. It doesn't say that the integral equals to the series, no. Okay, this test here does not say the series is equals to the integral. No, that's not what this test say. All this test say is they are both convergent or both divergent. So if the question is find if it is convergent or divergent, you can do integral test. If the integral test is convergent, then the series also convergent. But it doesn't mean they convergent to the same number. Okay, it doesn't say they convergent to the same number. Let's do one problem or two problems. Let's say, for example, we do number 8. Determine whether this series from n equals 1 to infinity of n squared e to the negative n cubed convergent. Then I will first say let fx be the continuous function x squared e to the negative x cubed. Note that fn equals to the n term. Okay, I need to show that this function is positive and decreasing. Okay, so need to show fx is positive. Second, fx is decreasing. Okay, so the first one, maybe instead of say need to show, let me just say claim instead, and then I prove that claim. So prove fx equals to x squared e to the negative x cubed. Okay, x squared is at least 0, right? And then e to the negative x cubed is greater than 0. Actually, it's greater than 0, but in fact we can say x squared is strictly greater than 0 for x greater than equals to 1, right? So because it's the product of two positive numbers, then fx is positive. Second, the first derivative of fx will be 2x e to the negative x cubed plus x squared times e to the negative x cubed times negative 3x squared. This is equal to, let me factor e to the negative x cubed out, then I get, actually I can take the x out also, 2 minus 3x cubed. Right? Now notice that for x greater equals to 1, then x is positive. E to the negative x cubed is also positive. And 2 minus 3x cubed will be negative when x is greater than equals to 1. So f prime x is negative for x greater equals to 1. That implies fx is decreasing on x greater equals to 1. This is to show that the continuous superposition function we have is satisfied the requirement that we have up here. that is eventually positive, eventually decreasing. Okay, now once we are done with that claim, then we go on with integral test. Now, integral from 1 to infinity of x squared e to the negative x cubed dx is equal to, don't forget this is limit involving infinity, so I need to use that's improper integral. X squared e to the negative x cubed dx. Then how to integrate this? I will say u equals to x cubed. So du is 3x squared dx. Okay, now then, the integral will be limit t goes to infinity of, this is 1, this is t cubed, and it will be e to the negative u du over 3. Which is 1/3 limit t goes to infinity of negative e to the negative u from 1 to t cubed, which is equals to 1/3 times 1 minus limit e goes to infinity of e to the negative t cubed. But that guy is equals to 0. Now, since integral from 1 to infinity of x squared e to the negative x cubed dx is convergent, then by integral test, the series from 1 to infinity is also convergent.
Professor, when we give our answers on the test, are we to write those words out?
Yeah, yeah.
Credit? Okay.
Yeah.
Because, is it okay?
Let me continue first. Because of the following, in our future sections, 11.4 or 11.5, one thing we will do to prove convergence or not is we show the other series. So we may be dealing with more than, we will be dealing with more than one series to show convergence or not convergence. So by saying that, oh, then since this is convergent, then the series convergence, you need to be precise which series you are talking about. Okay. You will be dealing with two series later on. Okay, you will be dealing with two series later on. Oops. Right.
To follow up, is it okay we abbreviate some of the things, or do you want us to use like the full word?
The one that you can abbreviate is the convergence and divergence.
Only that one, okay.
Yeah, convergence, you use this, divergence, I use this. We actually write it too much, right? We write it too much such that we'll just shorten it that way. Now, let me go back to this, to the question earlier. Now, we may be dealing with more than one series, okay? Now, so such that when you say the series is convergence, when you say the series is convergence, it is not clear this series here refers to this guy or that guy. Okay, so instead of saying the series is convergent or divergence, be explicit. say what series you are talking about. Okay. Sometimes
Okay.
I understand from the context, but when it comes to proof, when it comes to proving, there are plenty of things we need to show though.
Okay. Thank
Okay.
you.
Okay. Now, one thing before I go on further, something called P integral or P series. P series. P series refers to the series of 1 over n to the p. Now, I want to say that this series here is convergent when p is strictly greater than 1 and divergent when p is less than equals to 1. What's
Does
the
this
proof?
follow the same sort of logic as like
Integral
the P
test.
integrals?
Yeah, the P integral.
Okay.
Consider P integral. The P integral. So the term P integral is actually not in the book. I invented myself. But you get it right away. Okay. The reason P series is convergent or divergent is because of the P integral. Consider P integral from 1 to infinity of 1 over x to the P dx. Now we know that this is convergent when P is greater than 1, strictly greater than 1, and divergent when P is less than equals to 1. In fact, if you think about it, when P equals to 1, what do you get? When P equals to 1, you will get integral
X.
from 1 to infinity of 1 over x dx, right?
You get the harmonic series.
Yeah, the series version is harmonic series, right? So our P integral actually confirms what we know about harmonic series, that the series is divergent. Okay. Now, once we have these, then we are actually ready to do problems, further problems from the book. Let's say, for example, call this example 2. Number 12. We have 1 over 1. I write it 1 over 1. Actually, just 1. 1 plus 1 over 2 radical 2 plus 1 over 3 radical 3 plus 1 over 4 radical 4, 1 over 5 radical 5. Is this series convergent or divergent? And the way you argue will be solution at series 1 over 1 plus 1 over 2 radical 2 plus 1 over 3 radical 3 plus 1 over 4 radical 4 and on is equal to the infinite series from n equals to 1 to infinity of 1 over n to what power?
3/2.
To the power of 3/2. Right? Okay. You continue saying that is P series with t equals 3/2, which is greater than 1. Right? Okay. Now so this series is convergent or divergent?
Convergent.
Is
Oh, divergence. Oh, convergence. It's more.
convergent because it's
Yeah.
greater than 1. Okay. Now, how about number 14, by the way? Number 14. Number 14 is 1/5 plus 1/8 plus 1/11 and on. Is it convergent or divergent? Notice they don't ask you anymore if it is convergent, find the limit. They don't ask you that anymore. Now, let me ask you to rewrite this sequence, this series, using the summation notation from 1 to infinity. This is the summation 1/what? Can you tell? Notice that the denominator forms an arithmetic series, right? Arithmetic series. 5, 8, 11. The difference, the common difference is 3. So it will be 3n plus, in this case, plus 2. It's arithmetic series, so it follows a linear function. Okay, so 1/3n plus 2. Okay, now then how to prove that this is do you think this is convergent or divergent? You need to kind of make that decision early though.
I'd say convergent.
Why do you think it's convergent?
Because oh wait, ooh, and to the no, never mind. Let me think about it more.
It's actually divergent. It's actually divergent.
Yeah, I didn't
Because if
consider
n
the
goes to
powers.
infinity, right?
Well, the n will go to infinity. 3n plus 2 also go to infinity, but it's on the denominator though. Okay. Now the first reasoning is first method is when you do integral test. By integral test, you will see that integral. I skip the details. Okay. Integral of 1/3x plus 2 dx. Later on will go to infinity. As 1/3. So this is in t equals 1. So this is 5. And that's 3t plus 2. 1/u du. I use u equals to 3x plus 2. Yeah, fast forward, then I will get 1/3 limit t goes to infinity of ln u from 5 to 3t plus 2. 1/3 of natural log of I'm sorry, limit t goes to infinity of natural log of 3t plus 2 minus natural log of 5. But this guy will go to infinity. Right? Now then, by integral test, that series 1 over 3n plus 2 is divergent. Okay, so I do integral test, but I want to show you there's another way to look at that. There's another way to look at that. Notice that 1 plus 1/3, I'm sorry, 1/5, I'm sorry, 1/5 plus 1/8 plus 1/11 and so on and so forth is greater equals to 1/6 plus 1/9 plus 1/12 and on. I do this kind of comparison. 1/5 is greater than 1/6. 1/8 is greater than 1/9. 1/11 is greater than 1/3. Okay, so that series is, while the one on the right hand side here is actually the summation from 1 to infinity of 3n plus 3. I will factor the 3 out. And this looks like the following. Imagine if I make it k equals to 2 to infinity here of 1 over k. See the way I play with my notation. My purpose is to say that this series is greater equals to 1/3 of harmonic series. Right? But is a harmonic series. And therefore divergent. Then any series that is greater than that must be divergent. Okay, but this technique that I show you, the second technique that I show you here, has a lot to do with what you will learn in 11.4 called comparison test, which we already learned in improper integral section. Okay, if an integral bounded below by a divergent integral, then the first integral is divergent, so on and so forth. Okay, let's see number 20. Number 20, the summation of from 1 to infinity of 1 over n squared plus 6n plus 13. This one is very interesting. Is it convergent or divergent? Let me give you 5 minutes to think about it. Maybe 3 minutes to think about it. You will see what makes this section, or to be more precise, this sequence, the series problems becomes difficult because you need to pre-fill that if this series is convergent or divergent, and then find the reasoning behind it. Okay? Okay? When you try to show that it is convergent, the way you find the reason, the way you prove that is totally different from the way you prove if it is divergent. So there are times that you have to what's that? Decide first. Okay. Now, of course, the first method that I can show you here is by doing integral tests. That's limit t goes to infinity, integral from 1 to t of, let me complete the square at the same time, that's x plus 3 squared plus 4 dx. Is that right?
That's what I got.
Good. Plus, so I do substitution, u plus 3, u equals to x plus 3. So I get limit t goes to infinity of, instead of 1, now becomes 4. This is t plus 3. Okay, 1 over u squared plus 4 du. And if you remember, that's equals to, what will the integral be?
1 over 2 tangent inverse of u over 2.
From 4 to t plus 3. Right? Okay. But then this is equals to 1/2. Let me fast forward. Okay. When t goes to infinity, this is infinity. T inverse of that is pi over 2. Right? Minus tangent inverse of 2. Okay. Basically, this is finite, right? Basically, this is finite. Therefore, so by integral test, the series from 1 to infinity of that 1 over n squared plus 6n plus 13 is convergent. That's the first technique. The second technique, something that you're supposed to see later, okay, and it is by accident I can do this. This is n equals to 1 to infinity. The second technique happens to be more general. Notice that n squared plus 6n plus 13 is greater than n squared for n greater or equals to 1. Agree? Right? And so it implies the reciprocal will be less than. At the same time, it is still positive. Right? Okay. Now then, from here we can say, so after I show that, maybe I say it this way. From there, I go here, note So the summation of that series is less than equals to the summation. I use equal sign here just to keep myself safe in case, but at the same time, I also know that's non-negative, right? Okay, now notice that, but the sum, the series of 1 over n squared is convergent or divergent?
Convergent?
That's convergent by
P series?
P series, where P is equal to 2, then the series that we have the original question, this series is also convergent by comparison test. Okay, by comparison test. It has something to do with the fact that the following fact. I think I need to put more details here. I want to put more details there. That notice that the partial sum, maybe sk up to k, this sk as a sequence, the series, the k partial sum as a series is non-negative, right? It's non-negative, it's positive, and I want to show that it is increasing. Is it okay? If you see S1, the series, the sequence of S1, S2, S3, and on, right? That sequence is increasing. Why? You keep on adding a positive term, right? Okay, it's positive and increasing. Yet at the same time, Sk is bounded above all the time, by the sum of 1 over n squared. We don't know what number is that, but we know it's convergent. This thing here is convergent. Okay, so by monotonic bounded theorem, Sk is convergent to S. Is convergent. I don't know what's the S, so let me just say is convergent. That's actually a more proper argument. But in the next section 11.4, you will see we can use comparison tests. If it is bounded above by something convergent and that sequence is positive, that series is the series of positive sequence, then the series is convergent. Okay, let me stop here. Suggested homework. I'm not really done with this section yet though. There are more details I would like to fill in. 11.3. Number 3 to number 31. That's the main part. Things that I would like to do in future, things I would like to do on Monday is question like number 35, 38. Number 38. Let me show you what I do here. I hope then I can cut some time. Number 38, find the sum. Find the sum of the series 1 over n to the 5th from 1 to infinity, correct to 3 decimal places. Correct to 3 decimal places. In other words, the error is less than 0.0005. Okay, because we round it to 3 decimal place. Okay, so the last digit, the 4th decimal place is 5. Now, there's something we can learn, that the error, which is the absolute of actual sum minus the nth partial sum, should be less than equal to integral from n to infinity of the continuous superposition function. So that's what we will do. That's what we will use. Okay, that's what I will use. So how do I use that? Solution? I need to find the n. Need to find number of terms to add. Okay, so I will approximate the actual series by the first n terms. Okay, but then for that I need to have my error, which is set to be at most 0.0005. This has to be less than equals to integral n to infinity of 1 over x to the 5th dx. Now, how many terms should I do that? Okay, so let's show this. This is limit t goes to infinity, integral n to infinity of x to the negative 5 dx. I'm sorry, it should be t here. So this is limit t goes to infinity of negative 1/4 of x to the negative 4 from n to t. This is negative 1/4 t to negative 4. I'm sorry, I forgot the limit. Limit t goes to infinity of t to the negative 4 minus n to the negative 4. But this guy is equals to 0, so I get 1/4 over n to the 4. Now this guy has to be greater than 0.0005. Okay, multiply by n to the 4th divided by, actually if I do the reciprocal, I need to change the sign there. So my n to the 4th should be greater than 1 over 4 times 0.000. Am I right? Then we can compute it from there. Using my calculator, what do I get? 4 times 0.0005 to the reciprocal 500. So do the fourth root. So 500 to the power of 0.25, 4.7 something. So n has to be greater than equals to 4.7 something. So we just need use n equals to 5. That should be good enough. So as n as 5 will give the sum accurate to 3 decimal places. Okay, in other words, 1 over 1 plus 1 over 2 to the 5th plus 1 over 3 to the 5th plus 1 over 4 to the 5th plus 1 over 5 to the 5th, 5 terms. Now this is equals to the total sum with the error is less than, it's accurate to 3 decimal places. The sum here is accurate to okay, maybe I want to say more. 1 plus 1 over 32 plus 3 to the negative 5 plus 4 to the negative 5 plus 5 to the negative 5. I get 1, the sum here is 1.0366617. Okay, now when I add all of this, however much it is going to infinity, then the number will not be more than this. Okay, now basically from here, at most you add 0.0005 or less than 0.0005. Okay, this is accurate to 5 to 3 decimal places. So if you ask me, Thomas, what number will you use? How many terms you use? I will use 5 terms. Okay, well, anyway, this is where I will stop. I forgot that I give a test for my other class. See you then on Monday, but please try to do this 11.2b and 11.3. Okay, 11.2b and 11.3. The suggested homework. On Monday, I will do a bit of this 11.3, more details, and then I do 11.4 with 11.5. If possible, please read the book first. See you.